everybody, welcome back to Monte Carlo Methods. In today's video, we are finally going to finish testing our random number generator for uniformity and independence. And if you come back for the next video, we will finally start to learn how to simulate values from other distributions that are not the uniform 0-1 distribution. In today's video, I'm going to go kind of quickly through several tests just to knock some more out. I think that it will be enough detail for you to run them if you're interested, but if not, it will at least tell you what you need to be looking for if you want to read more about them. Now, so far, we have had runs tests for uniformity and independence. We also had the wonderful Kolmogorov-Smirnov test, which I think is the strongest out of all of these tests. Remember, our tests are just little bits of evidence for or against things that we want to accumulate into an entire suite of tests when testing our random number generator. But the runs tests that we have done so far, we have done runs of increasing numbers and decreasing numbers, and we have also looked at runs above and below the mean of 1/2 for the uniform 0-1 distribution. In both those cases, I didn't care about the length of runs, so maybe we had a number, the first number from a random number generator, and the second one maybe above that number, so we're starting an increasing run. And if the third number is above the second number, we are continuing an increasing run. And ultimately what we counted, though, was the total number of increasing or decreasing runs in a sample, or the total number of runs above or below the mean in a sample. And we have never cared about the length of those runs. And that's going to change right now. Our first test for today is a length of runs test. And we can do this test both in the case of up-down runs and in the case of above or below the mean runs. Today, I'm just going to focus on the up and down runs test. So let's look at our usual 21 simulated values that I got from the random number generator in R. And as usual, you want to read these values across rows. Order is important. So this is the first number simulated, the second, the third, the fourth, the fifth, etc. I want to look at runs of increasing and decreasing numbers here. And as in the other tests, I actually don't care about separating them into how many I had that were increasing of what length. I just care about the total length of runs, say of length 1, of increasing or decreasing numbers. You'll see what I mean in just a moment. So let's look at the first number here, 0.44 something. The next number is 0.07 something. We are going down. The third number is 0.3385 something, so we have turned it around and we've started going up. So when we start looking at this sample, we are looking at a decreasing run. It happens to be of length 1, and that's the thing I want to record. I don't care whether it's decreasing or increasing. Here is a run down of length 1. When we talk about increasing and decreasing runs, we count the length of the runs a little bit differently than we do when we talk about the length of runs above or below the mean. Because in order to say that you have increasing values, you need 2 values to get just 1 increase. So at all points here, if you're trying to count the length of runs, I would put like a little up arrow, a little like northeast arrow between these 2 values, and then like a southeast arrow between these values, and pointing up and pointing down. And really, you're trying to count the number of matching arrows in a row. So this involves 2 values, but it is a run down of length 1. Okay, so if we start now from this 0.07 something, the next number is 0.33 something, so we have begun a run up or a run of increasing numbers. The number after that is 0.88 something, so we are still increasing. But the number after that is 0.55 something, so we have now turned around and started decreasing. So these 3 numbers form a run up of length 2. Let's start with the 0.88 because things are turning around here. Going from 0.88 to 0.55, we are beginning a decreasing run. Then we have 0.29 something, which is below 0.55, so we're still decreasing. But then the next value is 0.414 something, so we have turned it around and started increasing. So these 3 numbers here are forming a run down of length 2. Again, the length is really the number of arrows. We go down once, and we go down again within those 3 numbers. If you continue, and I think you know what I'm going to do now, I'm going to say, here are 21 values I went through, and I happen to count 3 runs of length 1 Now, I don't care if they're increasing or decreasing. I just lump them all together. I also counted 7 runs of length 2 and 1 run of length 3, and I didn't count anything more. I didn't count any higher length runs on this particular slide. So if you'd like, this is a good time to pause the video and count your own runs and make sure you get the same numbers that I have, just to make sure that you know how to count them correctly. But if you're ready to go on, let's try to figure out what to expect if we really have independence here and uniformity. Suppose that capital X1, capital X2 through capital Xn is a random sample, which means IID values, a random sample of size n, from the continuous uniform 0, 1 distribution. My question to you is, in this sample of size n, how many up and down runs of length 1 do you expect to see? And then we're going to say of length 2, how many up and down runs of length 2 do you expect to see, and 3, and so on. And the highest run length you could have in a sample of size n is one big run of length n minus 1. So that would be if they just all went up from the beginning or all went down, you could get one big run of length n minus 1. I'm going to introduce some notation here. I'm going to let capital E sub I be the expected number of runs of length I in our n simulated values. Let's begin by trying for capital E sub 1. So in a sample of IID uniforms, once you actually have realizations and numbers and you count the increasing, decreasing runs, how many do you expect to see that have a total length of 1? To figure out how to count this, I want to look at an even smaller example, not my 21 values, but just 9 values. And for the purpose of making a nice slide that's not too busy, I am going to round off my values to 2 decimal places. You should not do this. You could end up with ties when you're trying to say, am I increasing or decreasing? And then you could deal with that, but you'd be making a different test. So here are my values, my 9 values. I have rounded them off, again, only to show them on the slide, but you should not be rounding for your computations here. I'm going to try to take this list here and underline values that start an up or down run of any length. Now, I know we care about figuring out the expected number of up or down runs of length 1, but bear with me for a moment. I'm going to underline values that start any length up or down run. The first value always begins a run of some length. It's 0.32 in this example. The next value is 0.64. So 0.32 is actually starting a run up. I don't care whether it's up or down. But if you look ahead to 0.52, that increase is starting to turn around. So actually 0.64 is also starting a run. 0.32 is starting a run up, and then 0.64 is beginning a run down. If I look at 0.52, the next value is 0.21, so we're still going down. So 0.52 is not starting a run at all. It's in the middle of a run that's going down, so I'm not going to underline it. But 0.21 is starting a run up because we go from 0.21, as you can see, to 0.88. And then after 0.88, I have 0.73, which means we've turned it around, and 0.88 is starting a run down again. So from 0.88, we go down to 0.73, and then we're going down again to 0.15. So 0.73 is not beginning a run, it's just in the middle of a run. But from 0.15, we turn it around and we're starting a run back up because the next value is 0.67. From 0.67, we are turned back around and then going back in the decreasing direction to 0.33. So 0.67 is also starting a run. And again, in everything I just said, I don't care about the lengths of those runs. I just underlined each value that is starting a run of any length. Now, let's go back to what we actually care about, which is to count the number of runs of length 1. How can you tell you have a number of length 1 by looking at my red underlines here? The first value of 0.32, we started going up to 0.64. 0.64, we started a run down. And so you can see that we have a run of length 1 because we have 2 of these underlines in a row. And anytime we have 2 of these underlines in a row, it indicates that a run of length 1 has occurred with the first of those two values. Actually, I don't have it in this example, but if we had 3 underlines in a row, then that would still be a way for us to count runs of length 1, because each underline is saying, turn it around, turn it around, turn it around, and is indicating that a run of length 1 is happening, even if we have a bunch of consecutive ones. So runs of length 1 are indicated by 2 underlines in a row. And note that the last value will never start an up-down run. When I'm here at 0.67, that is actually looking at the number in front of it, 0.67 is starting a run down to 0.33 of length 1. And then I can't tell if 0.33 is starting a run because I would need the next number to be greater than 0.33. And this is the end of my sample in this little toy example. Okay, so let's try to count these runs a little more formally. For I equals 1, 2, up through n, I'm going to define an indicator, capital I sub I, take the value 1 if x sub I is starting an up or down run of any length, and I'm going to define the indicator to be 0 otherwise. So if you go through the 9 values on the previous slide, every time I underline a number with a red line, that's going to correspond to the indicator there being 1, and every time I don't underline with a red line, that's going to correspond to the indicator being 0. Now, we noted on the previous slide that we have a run of length 1, either up or down, if we have 2 red lines in a row. And now that translates to us having 2 indicators turned on and being the value 1 in a row. How can you do that? You can look at pairwise products of indicators, because if you have an indicator that takes the value 1, and then the neighboring indicator takes the value 1, the product will be 1, and that tells you that you had 2 1s in a row. And if the product is not 1, then at least one of those indicators was 0, and you know you did not have 2 of those red underlines in a row. So the number of runs of length 1 in a sample of size n is given by the product of I1 times I2 plus the product of I2 times I3 plus ... out through in minus 2 times in minus 1 plus in minus 1. Because actually noting that final run that was started at position n minus 1 did only depend on us looking at a single value. We also always have that the first indicator is 1, so I really don't need to write capital I sub 1. I could write it as a 1, but this is an expression, and it's counting the number of runs of length 1. And if we want to know the expected number of runs of length 1, then we need to find the expected value of this sum of indicators. We called it E1, and E1 is the expected value of this sum of indicators. Again, I could plug in I1 equals 1 here, and let's do that and rewrite this as just I2 alone plus the sum as little I goes from 2 to n minus 2 of the product capital I sub I times capital I sub I plus 1 plus the indicator at position n minus 1. We can run the expectation through. We have a nice linear operator here. So this really comes down to, can we find the expected value of each of these indicators? This is back to our original runs up and down test, where we found these expected values where we were looking at these indicators. And I want to say the lesson number that's in, but my lessons are numbered strangely because I haven't put numbers on the in between our lessons. So I kind of don't want to say it because I might change those titles around, but I will link that video right here. Okay, so from our previous work with up and down runs, we do know that the expected value of I sub I is 2/3 for I equals 2, 3, up through n minus 1. And we also already computed that the expected value of I sub I times I sub I plus 1 is 5/12 for I equals 2, 3, up through n minus 1. And this is everything we need to compute our expectation here. So the expected number of runs of length 1 is going to be a 2/3 plus we have 5/12 here, and we've got n minus 3 of those terms, and we have a 2/3 out here. When you add these all up, you get 5n plus 1 over 12. Just for fun, in a sample of size 100,000, 5n plus 1 over 12 turns out to be 41,666.75. So that is what to expect in a sample of size 100,000, and we'll look at that later when we actually perform this test. So now how about the expected number of runs of length 2? I'm just going to get you started on this. This is some detail I do want to leave out today, but for finding the expected number of runs of length 2, you could look at products of indicators again. And if you consider starting in a position I minus 1 and say, I'm going to start a run there, but I do not want to be starting a run in the next position, or I would not be getting a run of length 2. I'd only have a run of length 1. But I do want to start a run in the I plus first position. So that would be a way to count runs of length 2. And you could be looking at indicator terms like this. It gets very messy very quickly. Fortunately, this has been worked out for us back in 1944. There's a paper by Levine and Wolfowitz. It's called the covariance matrix of runs up and down. And I'll leave the citation here if you want to check that out. So the formula they came up with looks like this. I did sit down to try to work this out one weekend, and I managed to get it. It's kind of tedious, and so I'm just going to leave it here. But if you want to check it out and plug in I equals 1, you should end up with 5n plus 1 over 12, which is what we got working it out our way. This formula holds when I equals 1, 2, 3, up through n minus 2, and the expected number of runs in a sample of size n of length n minus 1 is 2 over n factorial. This, at least the relationship seems right here. If n, your sample size, is large, then the expected value gets very, very small. And these are expected values, averages, like 2.5 children in a family. So it is fine that the expected number is something fractional. And in this case, I'm sure it's going to be much less than 1, obviously depending on your sample size. So in my 100,000 values from my random number generator, I went through and counted the total number of up-down runs of length 1, 2, 3, and I formed a table here. So these were my observations, and I had no more runs of higher length. So the end of my table here is basically showing you that the highest run length I saw was 7, and then I had 0 for runs of length 8 and 0 for runs of higher length. And these are the expected numbers computed using the Levine and Wolfowitz formula. I've got observed values and I've got expected values. So this is screaming for a chi-squared goodness of fit test. I've got categories. The different lengths are categories. And one thing before developing our chi-squared goodness of fit test, you'll recall that you don't want to be doing the test if the expected number of values in any one category gets below 5. And if you want to make that number just a little bit larger for safety, you could do that as well. So I don't want to be looking at certainly the category of 8 or 9 or 10 or anything like that, or even the category of 7. And 6 here is kind of low. So what I'm going to do is take everything 6 or greater and make that its own category. So my new table looks like this. I have all the same numbers, but this 48 came from adding up the number of observed runs of length 6, 7, and greater, of which there were none. So the only question is, how did I get this expected number? You actually can't add up the expected values that you saw at the end of my last table. Actually, you can, but you would need to compute the expected number of length 9 and 10 and 11 and go on forever like that. That's a lot of work, but note that we did count back in a previous video that I can't do this for because it's the same one I pointed to before, and I just found out that YouTube does not let me put the same video up there twice in one video. But in the same video, which is around lesson 5, we counted that the total expected number of up and down runs was 2n minus 1 over 3. Now, this is going to be made up of up-down runs of length 1, up-down runs of length 2, up-down runs of length 3, etc. So I can get, and I did get this number of 34.72 by taking 2 times 100,000 minus 1, all divided by 3, the total expected number of up and down runs, and then I took out what I counted for the expected number of up and down runs of length 1, length 2, length 3, etc. And that's how I got the 34.72 here. But now we are truly ready for a chi-squared test. I have 6 categories, and I've got observed values and expected values. We're going to use our same notation for the statistic we had last time. I called it W. It's going to be a sum as I goes from 1 to 6 of observed minus expected squared over expected. When you do that with my numbers here, I got approximately 7.83. Is this large? If it's too large, then we think that this number in here is getting too large. We think that what we're observing is too far away than what is to be expected, assuming independence of these values. This random variable here, we're actually observing it, so this is not a random quantity, but this random variable before being observed is known to have a chi-squared distribution with 5 degrees of freedom. You have to take one value away from the number of categories. This is a picture of a generic PDF, but this is supposed to represent my chi-squared 5 PDF. And we're going to say, what is too large before I'm going to stop believing that this is the right distribution. So what we usually do, if you know hypothesis testing, you know exactly what I'm doing here. But we're going to pick a value that cuts off some kind of small amount of the PDF up here. A typical value chosen is to cut off area 0.05 up here. And this value happens to be 11.0705. You could look this up in a chi-squared table. If you want to use R, you would type QCHISQ for Q chi-squared. That Q is for quantile, actually. And you would type 0.95, comma 5, the 0.95 being the area down below the number, and the 5 being the degrees of freedom. And that's how you can get this value. If you are interested in doing these tests in the future, you might want to pause the video, or after the video, try to find a chi-squared table or use some software and make sure you know how to find this number that I looked up, this so-called critical value. But this is the number that we're going to say is large because we want W to not be too large. Now, our value, our test statistic, did not get to be too large because we're defining too large to be above 11.0705. In other words, our test statistic did not get into this so-called rejection region. So we have passed this test for independence. That's like the null hypothesis. And if the test statistic is too large, we're going to fail the test for independence. We're going to reject the idea that we have independent values. So this is our test. This is our length of runs up and down. And we are done with the runs up and down test for today. Now, my other tests are going to be quicker still. I'm just going to talk about 2 more. So I'm going to talk about the serial test for uniformity and independence both. This is kind of an equidistribution test. This is something that the folks at IBM should have done with their RANDU, random number generator. What we're going to do is organize the output of the random number generator into vectors of length 2 or 3 or 4 or 5, and we're going to plot them as points in 2-dimensional space or 3-dimensional space or 4-dimensional space. We're going to envision them as points there. Now, I'm going to call my values U1, U2, U3, U4, etc., and I'm going to, again, pair them off in this case. I'm going to do this for vectors of length 2. And now I want to look at the unit square, and I want to kind of bin this up, and I am just going to draw some lines here. These are supposed to represent equal area bins, although you can adapt this test to non-equal area bins. And if I were to plot these points, if everything was nice and uniform and independence, this is one of those tests that sort of test for both at once, then you expect a certain number of these points to fall in each bin. Now, once we know the expected number in each bin, we'll have the observed number in each bin. We can compare the observed and expected with a chi-squared goodness of fit test. So I'm going to do my random sample from my random number generator of length 100,000 in 2 dimensions. I plot the points, and I chose to bin things up in a 20 by 20 grid. The number of bins you should use, this is a long conversation for which I do not have a satisfactory answer. I just wouldn't do anything too extreme. And I would probably look at several different, I might look at 10 by 10 and 15 by 15 and stuff like that. But I definitely wouldn't do data snooping. I wouldn't just do it until I got the result I wanted. So I would look at several and try to draw a conclusion about them. And I think if you're too extreme, looking at like a 2x2 grid or a 1,000 by 1,000 grid, that's when you're really going to have problems. So take it with a grain of salt. But I use a 20x20 grid. I have 50,000 points or ordered pairs. Under the assumption of uniformity and independence, I expect to see 125 values in each two-dimensional cell. And so because I've got 50,000 points and I'm dividing by 400, which is my total number of cells in my 20x20 grid, I am going to form a statistic. I've got observed numbers in each cell, and now I have the expected number in each cell, which is 125 for all cells. My test statistic, I'm going to call it W. This is going to be the sum as I goes from 1 to 400 of observed minus expected squared over expected. And this is going to be the sum as I goes from 1 to 400 of observed minus 125 quantity squared over 125. I am not writing out my list of observations, but when I did this in total, I got 422.4 approximately. Now, is this too large? We do want to look at a chi-squared probability density function with 399 degrees of freedom. I'm going to try to capture area 0.05 out in the right tail and say that when I'm above that value, that is going to be too large. The critical value here is 446.57-ish. Again, I got that by typing Q, CHI, SQ, quantile chi-squared, and then a 0.95 for the left-hand area, and then the degrees of freedom parameter. My number of 422 is not up here. It is not above 446 point something. So we did not fall in this rejection region, which means we passed this test for uniformity and independence both, because both of that went into what we should expect in each cell. I'm not going to show results here, but I did try this for many other grids. Notably, I did fail the test when K was 2. So when I had a 2x2 grid, I did not quite make it. But I passed in a whole lot of cases. And all of this has to be taken with a lot of grains of salt, with a whole shaker of salt. And all these tests really should be looked at together. Again, you don't want to be accused of data snooping. You don't want to say, okay, I failed, but I passed if I change to this grid size. So really take a look at a whole bunch of grid sizes. And as I said, the extreme values of really few bins and way too many bins are where you're usually going to have trouble. So once you sort of look somewhere in the middle, whatever that means, if you look around it, if you go a little bit below the 20x20, a little bit above, and things are staying consistent, then I personally would feel okay about this test. The third and final test for today is the autocorrelation test. Now, if random variables x and y are independent, the covariance between them, which is defined to be the expected value of the quantity x minus its mean, this mu x stands for the expected value of x, times y minus its mean, is 0. And I do have a video up on covariance, which should be over here. And if you haven't seen it before, you probably need to look into that in order to understand this test. So this covariance is 0 if x and y are independent. And essentially that comes from the fact that if these quantities are independent, then you can factor the expectation. And the expected value of x minus its mean, as you run the expectation across, you get the expected value of x, which is just mu x, and the expected value of the already expectation taken mu x. That's the expected value of a constant. So you will get mu x minus mu x for the individual expectation here, assuming you can factor this, which comes from independence. Now, the reverse statement is not necessarily true. You can have random variables x and y with a covariance of 0, and yet they are dependent. And I'm going to spare you an example of that because that's not really the point here. We're not doing general statistics or mathematical statistics, and I am trying to finally get to the simulation. So covariance of 0 comes from independence, but does not imply independence. Now, correlation, if you've heard of it, is just covariance that has been rescaled to be a number between -1 and 1. Because if you look at covariance and it's not 0, and you say, wow, this is a large number, or really large in magnitude but negative, it's difficult to talk about what large actually means. So if you rescale it to something guaranteed to be between -1 and 1, then it is easy to talk about what a large correlation is, or a small correlation, because the largest value is 1 and the smallest is -1. The correlation between x and y is defined to be the covariance divided by the square root of the product of the variances of the individual random variables. It's easy to see that if the covariance is 0, this correlation is 0, and the only way the correlation could be 0 is if the covariance is 0. So random variables are said to be uncorrelated if their correlation is 0, equivalently if their covariance is 0, even if you never get to looking at correlation. If you have a covariance of 0, you can say that your random variables are uncorrelated. And that is consistent with independence, but not enough to say you have independence. But the other direction, if you see evidence for correlation, then you're seeing evidence for independence, because if they're independent, they should be uncorrelated. And if you're seeing correlation, then they couldn't have been independent. So that's the idea behind the autocorrelation test. We are going to assume that our random number generator is producing independent values, but we're going to get suspicious if we see too much correlation. So back to the idea of the autocorrelation test, because that was a little aside about covariance and correlation. I've got some random number generator output, capital X1, capital X2, etc. And I want to consider the autocorrelation here. Now, auto means like self. We're talking about correlation of values in the sequence with other values in the same sequence. So that's the auto in the autocorrelation. And we can look at values that are next to each other and how correlated they are. So values that are adjacent, we would call that a lag 1 autocorrelation. And if values are 2 apart, we could talk about a lag 2 autocorrelation. In general, we're going to talk about a lag J autocorrelation. I'm going to call this rho. This is a rho, not a P. It might be hard to tell in my handwriting. Sub J. This is going to represent the correlation between xn and xn plus j, which is, of course, the covariance over the square root of the product of the variances. Now, if these are IID, then each of these variances are identical. Not only is the variance of xn equal to the variance of xn plus 1, but they're both equal to the variance of just x1. So if you've got the variance of x1 times the variance of x1, you get the variance of x1 squared, and under the square root, you're going to knock out that square root, and we're going to have a simpler expression. The autocorrelation of lag j can be written as the covariance between xn and xn plus j divided by the variance of x1. The covariance between xn and xn plus j is an expectation formula that I wrote down. And if you multiply things through and run out the expectation, or you visit that video that I have on covariance and correlation that I can no longer point to, then you would know that we can write this numerator, this covariance, as the expected value of the product of these random variables minus the product of the expected values. If things are identically distributed, then both of these expectations should be the same and be the same as the expected value of x1. So I'm going to replace this product of expectations with one expectation for x1 squared. And in particular, for the uniform 0-1 distribution, the expected value for any one of the values is 1/2, and the variance for any one of the values is 1/12, which you may know already, or you might have to go check out. But that's the variance for the uniform 0-1 distribution. So if I rewrite things here, I have 12 times the expected value of a product of two random variables minus 3. This is what I'm calling the lag J autocorrelation, and we can estimate it from the data, or in our case, our simulated values. I'm going to call it rho sub j with a hat on it, and I'm going to replace this expected value of x1 times xj plus 1, which is a probability weighted average. I'm going to replace it with an actual average of terms like this from our sample. So for example, I'm going to look at x1 times xj plus 1, but then I'm going to look at x2 times xj plus 2, things that are j units apart, then x3 and xj plus 3, and average those. And my sum only goes up to n minus j because I don't want to go off the end of my sample here, although you will see some people estimating autocorrelation by kind of rewrapping around to the first indices. I'm also going to just do a straightforward average, So if I have n minus j terms, I'm going to divide by n minus j. Those of you who have taken mathematical statistics might wonder if this is an unbiased estimator. It is not, and we could adjust this denominator for unbiasedness to make it an unbiased estimator. But I'm just going to leave it as straightforward as possible here and as intuitive as possible here. So this is my estimator for the lag J autocorrelation. Whether or not it's a good estimator is an entirely different question. Because this estimator does depend on n, the sample size, I'm actually going to start calling this rho sub j hat. I'm going to call it rho sub j comma n hat. And I claim that because of how it's formed with this sum in here, that it actually follows under the assumption of independence of these values and uniformity, because I've already plugged in some numbers related to the uniform distribution. I claim that this estimated lag J autocorrelation, which is a random variable at this point before I actually have the numbers, is, by the central limit theorem, approximately normally distributed for large sample sizes. Now, that is a serious amount of math stat work that we would have to do to show that. But because we're in a simulation class, let's actually look at some simulated values. I simulated 100,000 values for my random number generator in R, and I computed this when j equals 1, and I got a number. That one number has no distribution. So I simulated a new 100,000 values and did it all over again, and I got a number, another estimated lag 1 autocorrelation. And I did that all over again. I actually did it 100,000 times, and I made this histogram. You can see that it looks normally distributed, and I did fit a normal curve over it by using maximum likelihood estimators for the parameters based on these data. You don't have to know what that is, but I basically took the actual mean and variance of my simulated autocorrelations and used those as parameters for a normal curve that I superimposed over the histogram, and you see that we have a really nice fit. So this is me trying to say we have a central limit theorem here. Things are not independent, things are wrapping around, but I've mentioned in the past that there are versions of the central limit theorem that can be used in non-IID cases. And this is just some evidence, some convincing. It's not evidence, but to convince you that we do see a normal distribution. I did it again when j was equal to 2. You know what? In both of these pictures, I did not look at the full autocorrelation. What I looked at was the average right in here. And this is why they are centered at 0.25. In fact, I can show theoretically that the expected value of this is 0.25. And when you run it through with all these other things around it, I can show theoretically that the expected value of the lag J autocorrelation estimator is 0. That's not what I plotted. I plotted just a part of it. So I'm not centering these at 0. These things are not being centered at 0. But here's my j equals 2, and here's another one at j equals 5. I bet you hardly even noticed that the slide changed, but it did. And all of these are looking nice and normal. And in all cases, I superimposed a normal density to further make myself feel better about skipping the math stat in here. But as I said, we could show, and it's well within our skills in here, to find the expected value and variance for the lag J autocorrelation estimator. I just don't want to take the time to do it. The expected value is 0, and the variance is 13n plus 7 over n plus 1 quantity squared, obviously. With that, I can claim that I'm using a version of the central limit theorem to say that for large n, the estimated lag J autocorrelation is approximately normally distributed with mean 0 and variance 13 n plus 7 over n plus 1 quantity squared by, again, a version of the central limit theorem. Now, if the estimator is too far from 0, we're going to reject the idea that the sampled values are independent. you'll note that the test depended on the uniform 0-1 distribution, because that's how I got that 1/12 in there and that 1/2 in there. And that did affect the statistic that I'm putting together. So this isn't a test purely for independence that stands alone from uniformity. It does depend on the fact that my values are assumed to come from a uniform 0-1 distribution. But we are going to standardize this approximate normal thing. I'm going to call that Z sub n. And we're going to reject that our values are simulated in an independent way if this falls outside of the interval from negative 1.96 to positive 1.96. Those two magic critical values that capture area 0.95 in the center for a normal 0-1 distribution. For my sample of size 100,000, we were well within this range for j equals 1, 2, up through 10. Those are the different lags I tested for autocorrelation. And when I say this, I don't mean to say we were outside the range. These are just the values that I looked at, and I stopped at that point. So we are finally done testing our random number generator for uniformity and independence. In the next video, we're going to learn how to start simulating from other distributions, how to turn our uniforms into other things. And in the next video in particular, we're going to focus on discrete distributions. So I really hope to see you in the next one.